MSE is the L2 norm squared. May is the L1 norm. Weight decay is the Frobenius norm of your parameters. Every time you write a loss function, you are choosing a norm. Norms are rulers. They measure the size of a vector or matrix. 3 vector norms dominate machine learning: L1, the sum of absolute values; L2, the Euclidean length; and L infinity, the maximum absolute value. For matrices, Frobenius, spectral, and nuclear. Learn these 6 and every regularizer, every loss, every gradient clipping rule makes immediate sense. For vector v equals 3, 4, L1 norm is the sum of absolute values, 3 plus 4 equals 7. L2 norm is the square root of 9 plus 16 equals 5. L infinity norm is the maximum absolute value, 4. Different rulers, same vector. The unit ball, the set of vectors with norm exactly 1, reveals the geometry. L1 unit ball is a diamond. L2 unit ball is a circle. L infinity unit ball is a square. The general LP norm is the PTH root of the sum of PTH powers. As P increases from 1 to infinity, the unit ball morphs from diamond to circle to square. The L0 pseudo-norm counts non-zero entries but is NP hard to minimize, so L1 is used as its convex relaxation for tractable sparsity. 3 matrix norms matter. Frobenius norm, square root of the sum of all squared elements. Equivalent to the L2 norm of the vectorized matrix. Equals the square root of the trace of a transpose ANP, linear LG, norm, A, returns Frobenius for 2D arrays. Spectral norm, the largest singular value of A, controls how much a unit vector gets stretched. NP, linear LG, norm, A, or equals 2. Nuclear norm, sum of all singular values. The convex relaxation of matrix rank minimizing the nuclear norm promotes low-rank solutions. Used in matrix completion problems like Netflix. Condition number is the ratio of largest to smallest singular value. Large condition number means numerically unstable. All matrix norms satisfy submultiplicativity. The norm of a product is at most the product of norms. 4 applications. 1. L1 versus L2 regularization. L1 penalty drives weights to exactly 0 sparse models. L2 penalty shrinks all weights but never to 0 smooth models. Use L1 when you want feature selection, L2 when you want stable small weights. 2. Gradient clipping. When the L2 norm of the gradient vector exceeds a threshold, rescale the gradient to have norm equal to that threshold. Preserves direction, limits magnitude. Standard practice in RNN and transformer training. Torch. NN. Utils. Clip_grad_norm_ does this. 3. Batch normalization divides activations by their standard deviation. A scaled L2 norm of the centered batch. 4. For your 96,000 device monitoring network, compute the L2 norm of the residual between each device's metrics and the SVD low-rank reconstruction. Devices with large residual norms are flagged as anomalous. 6 NumPy patterns to memorize. L1, NP, linear LG, norm, V, or equals 1. L2, NP, linear LG, norm, V, the default. L infinity, NP, linear LG, norm, V, or equals NP.inf. Frobenius for matrices, NP, linear LG, norm, A, quote fro quote, or just NP, linear LG, norm, A, for 2D. Spectral, NP linear LG norm A or equals to nuclear sum the output of NP linear LG.svd with compute _UV equals false. For normalization, divide a vector by its L2 norm to get a unit vector. For row-wise matrix normalization, divide by the row norms with keep dims equals true. For Euclidean distance between two vectors, NP linear LG norm A-B. For batch pairwise distances, Skippy spatial distance, see dist. 3 rules to know. L1 for sparsity, L2 for smoothness, L∞ for worst-case bound. 1 formula: the LP norm is the PTH root of the sum of PTH powers of absolute values. 2 exercises: compute all 3 vector norms for verses equals 3, 4, 0, 1, 2 by hand, then verify with NumPy. Check the inequality. L2 norm is less than or equal to the square root of dimension times L∞ norm. Second exercise: for a random 4×3 matrix, compute Frobenius, spectral, and nuclear norms and verify that Frobenius is greater than or equal to spectral. You now have the complete norm toolkit, the formulas, the geometry, the NumPy calls, and the AI applications. Loss functions are norms of residuals. Regularizers are norms of weights. Gradient clipping is norm rescaling. Anomaly detection is norm thresholding. These are the mathematical objects that every loss function is actually computing. Subscribe so video 16 is ready. Post your MSE, May, weight decay norm answers in the comments. See you in video 16.